Our presenter today is Magdalena Markovic from Uppsala University. She's a researcher at the Uppsala University, and she earned her PhD in solid earth physics, which is applied geophysics, from the same institution in 2022. So we congratulate her. Her primary research focus lies in hard rock seismics for mineral exploration and the development of machine learning workflows to identify features of interest within the seismic datasets. She's an active member of EAGE, serving as a committee member of the technical community group, Mineral Exploration Geophysics, as well as AGES, the Association of Geophysicists and Environmentalists of Serbia. Teaching is her passion, and she's honored to be a part of this hackathon where she will inspire, introduce the generations to the world of geophysics. A little bit of what today is going to be about. So what is this basics of geophysics? What's the goal of today's session? It's to kind of guide you that are here present or that will access this webinar later, and professionals on different levels of backgrounds through the geophysical methods and demonstrating his power in understanding planet Earth, which is really cool. The lecture will deliver both theoretical background and applied examples from data acquisition through data processing and finally data interpretation. The examples of the newest trends, such as integrations of AI tools and robotic platforms within the geophysical surveys and data handling, will also be presented. What I'd like to mention is that once Magdalena is done presenting, we will have a Q&A session. It will be moderated by myself, so kindly put your questions in the chat box, and we will try to cover all those at the end of the session. Without further ado, I would like to stop sharing the screen and passing it over to Magdalena. Thank you for being here today.
Thank you, Gabriel. Now let me share the screen and you will tell me if everything is all right.
Yes, we see it. Just need to put it in full mode.
Do you hear me also?
Yes, we can hear you and we can see it. Okay,
perfect. Okay, hello everyone. As Gabriel said, I'm very happy to be part of this year GeoEnergy Hackathon, and it was really like when he invited me. It was really interesting to hear about the concept. I was not aware of it, honestly. I was not aware of it, that it exists, and it's been already third year, if I'm not wrong. And I'm very happy that something like this is happening. But before we start, I want to just say a few words about myself. Gabriel covered most of it. So I earned my PhD last year here in Uppsala, at Uppsala University. Official degree is called solid earth physics, but essentially is applied geophysics. And my thesis work included the application of reflection seismic method for mineral exploration, and also some machine learning workflows developed within the seismic data sets, which I will present something of that today. And my previous education was at University in Belgrade in Serbia as well. It was applied geophysics, but there I was dealing with different kind of data sets, mostly applied to near surface geophysics, which I will explain to you a little bit later. And my research interests are currently hard rock seismics and AI applications within seismic data sets, and also I'm very I very much like to work with crustal case studies. I started some ongoing project currently, but I hope I will in some next years or GeoHackathon I will be able to present some results from those too. So you can find me. This is a LinkedIn link for my profile. If you want to contact me, you can find me here. And this is photo of myself in one mining city in Sweden, where I will present the data set we surveyed from that site. And now, after saying something about myself, I also want to say something about our team here. This is not promotion, it's just like to make you curious what we're dealing with here in Sweden. So if you want to find out more about our projects and our fieldwork activities, you can scan this QR code and you can see all the photos we are posting. We opened it recently, fairly recently, so not all fieldworks and projects are covered there, but yeah, we are trying to update it as much as possible. So basically, I'm part of applied geophysics group, but specifically for reflection seismic. And what we are researching here about, like we have projects in near surface geophysics, which are mostly involved we're mostly involved with infrastructure projects, landslides, and mineral exploration. Then we have recently very big CCS project where we were dealing with the land seismic acquisition and data processing. And as well, our group has many case studies on crustal scale projects, for example, like mapping of Moho discontinuity. Also, we are dealing with instrumentation development. So we have few instruments developed here at our department. I will show some of them in the presentation, such as Landstreamer state-of-the-art system. And the other one is GPS time tagging system, which is patented. That means this system is made for time tagging of seismic data, active seismic data sets, and to provide GPS signal in underground. So that means in whichever tunnels, either for infrastructure or mining tunnels, you can use this GPS system. And we also we have publications of this as well. And besides this, we also are developing software solutions, and we have numerous in-house algorithms developed here for seismic data modeling, processing, and interpretation. So now, before I start, one more thing. I really want to know more about you, and I created this QR code with Mentimeter, and I kindly ask you to scan it and answer it. It's completely anonymous survey, and I'm currently attending academic teacher training course within Uppsala University. So this is we have one task to make a pedagogical project, and I really thought like this kind of presentation could be a very good topic for the project to present online to broad public about the basics of geophysics. So if you can just quickly scan it and answer, it would be very good. And I hope most of you had time to do so. And I really thank you for this. And there will be a few more questions during these presentations, like not too many, but I would like to hear your feedback as we go on. So let's start. What is geophysics? So I was like thinking about how to organize this lecture, and it's like, okay, like when you talk about basics of geophysics, let's assume that we have different backgrounds, so we have to start like from basic questions of what we consider by saying geophysics. And you can see some definitions that pops up from Britannica Dictionary, and yeah, it says like, oh, it's a branch of science that deals with physical movements and forces in the earth, or like it's a major branch of the earth sciences that applies the principles and methods of physics to the study of the earth. And if you just read this sentence, you can imagine how big the field is. And so to cover all in 1.5 hours, it won't be really possible, but I will try to guide you to some examples and to show you like some interesting stuff and interesting sides of geophysics. Unfortunately, I won't be able to cover all, but you will get the overall idea. So let's see what can we observe. So these are some figures of the Earth and structure of the Earth. So geophysics actually showed us how can we map the structure of the Earth, and some of you probably heard that we could actually map all the layers of the Earth by propagation of the seismic waves that were generated by earthquakes. So that was one of the first ideas, how we got like idea that Earth has many layers, and how is the structure of the Earth's interior. You can see on this right-hand photo figure, if you see the boundaries A, B, C. So we have here is the continental crust, and then here you have the ocean, and then again on this side continental crust, and you can see the thickness, and then from A to B you have a mantle, B to C is outer core, and this is inner core. And then you can judge here by numbers what is actually the radius of the Earth. And also from another aspect, like we know that Earth is quite a dynamic planet, so lots of things are happening inside of the Earth. And when we talk about, for example, magnetic field, we say that Earth is self-sustained dynamo. So you can see on this bottom picture on the right side that like how the currents are flowing, convection currents, like in the Earth's outer core, how they generate all the force and how they support the magnetic field. So you can get the idea how actually complex it is. And on the other way, like when we look into gravity field, we get to know, like geophysics provided, like, okay, Earth is really not a sphere. Like it's not either like something like elliptical, whatever, how they were describing it. There is a name geoid, and this was actually one figure, if you look from the bottom left side, from a NASA site, from the GRACE project, from the satellites where they measured the gravity field of the Earth. And yeah, you can conclude where the denser parts were not, and that the Earth is not really spherical shape. We call it geoid. Yeah, so yeah, our planet, we concluded that there are many complex processes within the Earth and within the Earth's interior that we can see on the surface as well. And on the left-hand side, you can see a very well-known figure about tectonic plates on the map and where their positions. So we know these contacts that we have, for example, a lot of volcanism and other activities, seismic events. So everything is like dynamic on those plate boundaries, how we call it. So you can get the idea like what is happening, that plates when they meet each other, they can either spread or they can subduct, which is like subduction is when one plate is going under the other one, and then that can cause like either volcanism or seismicity and so on. And there are a lot of other stuff, but I will just try to keep this as much as possible basic. So now let's jump into geophysical methods. So when we talk about geophysics, so we have, okay, physics is one of the words in the word. So when we talk about geophysical methods, we have to mention physical properties of rocks. So there are many physical properties of rocks, and every method is created to map some of them. So we have to mention that different rock types have different physical properties, and that's how we differentiate them as well. But also, like when you look at on larger scale, like different geological layers, boundaries, they create contrasts in properties. So that's how we can see, okay, the changes or anomalies where the layer changes composition. So basically, like we have, like I listed here several. For example, density is the key physical property for gravity method. Then we have magnetization for magnetic method, resistivity, geoelectrical, then reciprocal to resistivity, electrical conductivity for electromagnetic method, and elastic properties for seismic method. And to acquire those data, so we call something that is called data acquisition. So data acquisition is designed to map all of these properties. So you basically, if you know in which geological setting you are more or less, you would choose each method. Some methods are advised to combine together, so we can so that we can use them and complement each other. So we use like acquisition of geophysical data. We use them to map these properties and study their contrasts at different scales. So we can measure basically from rock samples to like crustal scales. And as you saw, like we could see even how we could even map the Earth's interior. And when we talk about processing of the geophysical data, so once you acquire data, you have to handle them, and that is like, let's say, the main like overview goal is to increase signal to noise ratio. And of course, every method has certain corrections you need to do in order to obtain signal, desired signal. Finally, when we talk about interpretation, so we, as I said a minute ago, we want to integrate all geophysical existing data or existing knowledge, like geological knowledge or from a borehole, whatever exists in the area, or we combine few methods. So it's depends what is the goal of geophysical survey. But for example, if you have some very big, large scale surveys, you would, and then you want to narrow down precise place where you would, for example, for CCS projects, carbon capture storage, where you want to find the salt dome, to narrow down positions where you can drill and inject and place your pumps and inject CO2 in the ground. So you have to really like start from larger scale studies, and then you narrow down with more high resolution data acquisition. So that's like all within, let's say, all the data would be used later to interpret, okay, we narrow down where we want to, for example, do something regarding the project we are doing. So this is like very broad explanation, but I hope you got some ideas. So I wanted to put this very interesting sentence I heard a few years ago, and I really like it. It is Milutin Milankovic, was one very well-known Serbian geophysicist, climatologist, and maybe you climate scientist, and maybe you heard of him for Milankovic cycle. And he said that everything is recorded in rocks. And I would agree with him, because everything is recorded in rocks, and it's up to us as scientists to find instruments to read what is recorded in rocks. So I really like this sentence. That's why I wanted to share it with you. Okay, now one more question. I want to ask about your experience with the geophysical methods. Maybe you don't come with geophysical background, but you still took some courses in geophysics. So I would appreciate if you can scan this QR again and answer. It's like you can choose one or multiple answers if you use more geophysical methods. So like experience in the sense also field work or processing of the data or understanding. I just wanted to know if there is anyone who had something to do with geophysics here. I hope you had time to scan it, so I will try to move on. Okay. I will start now with the magnetic method, and I really like this figure. I used in most of my presentations when I was student, when I was talking about magnetic method. So what you see here is Earth's magnetic field, and this cool illustration here shows the magnetic field lines. And I want to talk about it a bit because it's very interesting. I mean, it is some of the most interesting things when I was like a bachelor and master student. It was fascinating to me how it works. And so I want to first start like, what are magnetic storms, and how do we measure variations of magnetic field? And this, I wanted to point that because I want for you to see that geophysics is not only like, okay, we survey for, I don't know, oil and gas, like very applied. So it's also, it has those fundamental components where we want to understand a bigger picture of the Earth. So this is one of the methods that I can show that it has like from bigger picture to like very applied examples. So here, like, assume that this is the sun. So we see that the magnetic lines which are faced over sun, they are suppressed compared to field lines that on the other side, which are like elongated. So this figure is quite, it's cut on one side. So you see, like, it's like, we call it magnetic tail. And what is interesting here is when there is because sun is quite also dynamic, and there is all like a branch of science like physics of sun. So to simplify it, when you have like so-called eruptions on the sun, so it can sometimes happen that a large amount, like big storm, like solar storm, attacks the Earth, and then we can feel it on the Earth. But what actually protects us from direct radiation is the so-called Van Allen radiation belt, and it's probably somewhere like a closer. Now I don't have that figure where you can see exact position, but it's more towards the inner side of the lines. So that's a special belt that absorbs most of the Earth's radiation. But when we have a really strong solar storm, then those radiation belts, they cannot really keep all the energy. So some of the energy goes into the Earth, and that's how we got this aurora lights phenomena. And then you see here, I put just a graph, like a graphic of aurora lights. Now this is borealis. So on both sides of the Earth, you have on a polar lights, which we call the aurora borealis, and aurora australis, which you can see in southern hemisphere, but it's more accessible on north hemisphere. And you can see them in many colors, and that depends with which gases they are mixed in the atmosphere. And then what is very interesting again are magnetic poles. So you can see there's one here and one here, and they're often confused with geographic poles. So magnetic poles and geographic poles are not the same thing. And what we need to know here is that magnetic poles are not stable. So they're rotating, and also north and south magnetic pole, they're independently rotating all the time. They're not sync, and sometimes they can really go off a lot, and that like moving we call excursion. And in the past, what we can, again, I will refer to Milankovic quote, what is recorded in rocks is that we have magnetic poles reversal. That means that southern pole becomes northern pole, so they reverse. So in our existing history, we could not spot any. So there is like excursionists, for example, when it comes to the point that it will reverse, but it goes back. So since the last magnetic pole reversal, it's been a lot of time passed, and from studies that scientists conducted, they couldn't find really some periodical occurrence like that. It happens in some certain periods, so it's not, they could not conclude so much from the data. So we can for now judge that it's kind of a random occurrence. But yeah, so this is what I wanted to tell about Earth's magnetic field, and I hope it's a bit clarified some things about this. And now let's see response of magnetic field. So here on the right side, you can see one of the graph here is for the gravity field. I won't cover that here, but let's compare it like on this example directly. And here is the response of magnetic field. What we have here is, you can see the density of the body that you want to detect is lower than density of surrounding area. So what would you get in that in this case is that you will get like a kind of negative response here. But on gravity, you see only one peak here, or how would you say, anomaly, negative anomaly. But here you see like double. Like, why do we see? Because we have to understand that that Earth is like a big magnet, and magnet is a dipole. So that's very important. That's why we have this kind of response. And then when there is a transition between two different environments, like layers, let's say, we will have like a response like from the contact. It will be like one peak, high peak here. And for gravity field, we see like a smooth transition. And when in the case, like when we have a response from the contact from low to high density or magnetism. And here, like when we talk about body that has very high, that is very magnetic, but the surrounding is not, then we will have a positive anomaly. So this is basically like, also like maybe you can like compare it directly with gravity field. And obviously you can see that here we have to also do some kind of correction later on with the data. So yeah, this is formula for magnetization. And here we can introduce magnetic susceptibility, which represents degree to which body can be magnetized by external. But when you expose the body to external field, how much degree to which body can be magnetized. So this is like external field, and this is magnetic permeability for vacuum, mu0. That's a constant, and this is how much it's value. So on the other side, like we can measure this magnetic susceptibility in the field, and this is one of the photos that I took from the field in Denmark last year when I took students for fieldwork. And because we could not find any outcrop in the field, we were measuring randomly on some rocks we could find. And then there is like, you can find in literature ranges of magnetic susceptibility and which rock type corresponds to each range. These are like these things have the susceptibility meter have this one has, I think, 5 millimeters penetration, obviously, because you see that this rock is not homogeneous. If you place it, if you measure on one side and another side, it might not be the same value. So you have to be careful because it's different mineral content concentration and so on, and that is what gives a different value of susceptibility. So, like, there are different types of magnetization, and like how, so magnetic susceptibility also depends directly from magnetic permeability, and in the case like when we don't have non-magnetic minerals, for them ratio is usually is 1. And what means like types of magnetization, so how the field lines will orient. So if we have here ferromagnetic domains, that means that all domains are the same size and oriented in one direction. When exposed, this sample, let's say when it is exposed to weak external field, it tends to align, but it's still like it's still not aligned in one direction. But when you expose it to strong external field, then because it has ferromagnetic domains, it will align in the direction of the field. So there are different types of magnetizations. For example, like if we compare ferromagnetism and ferrimagnetism, we see that they don't have only opposite lines, but they also domains. They also have one is shorter, one is longer. So there are several types. Like depends which type of mineral is it. So when we talk about data acquisition, so you can survey on land, we can survey from the air, or we can survey in water, like marine acquisition. And this is a photo from yesterday. Part of our crew is having a field course, took students for a field course in Denmark, and we are teaching there also magnetic methods. So this is one of magnetometers we have here in our group. And here, yeah, so this is for the purpose, I think they wanted to survey something for archaeological purposes, but I will get there in the next slides. What is important when we survey, for example, land survey? So when we have our instruments, so usually you use two instruments. One is so-called base station, and it is very important that you place this base station so it is not so it has to be fixed in one spot, and it will continuously measure changes of magnetic field. And it is very important to place it in a very calm area, so you would not place it next to, for example, fence which has some kind of iron on it or something like that. So you would really try close to power lines or whatever. So you would really try to avoid that. You place it somewhere in a calm place, and then you can set on your device how many samples how many time between each sample will take. So you want to, for example, to sample every 10 seconds your variation of magnetic field. So this is basically your sensor, and here is the brain, the computer, and this is GPS. So basically every 10 seconds you store the data, and then you can plot it as a function of the time. And you can see, once we had 2 years ago, we had a case that we had base station when the day when we had the magnetic storm reported, very, very high activity, solar activity, and we could obviously see higher values there. So when you plot the data from the base station, we call it general variations of the field, then you can see the changes, and then if there are some like very high values, so you can assume maybe some stronger solar activity happened. And that's why I wanted to introduce you to those fundamentals before getting here, so you get the idea what it is. And then for the land survey, because obviously like it is magnetometer, so you're not supposed to have magnetic things on yourself. And I had last year a student who came with Dr. Martin's shoes, and of course, I mean, it was we tried fun, like to measure what their differences, and it also depends if it's close to your sensor. And there were some students who had metal frame of glasses, and also we tried to experiment, okay, how much this would influence on your measurements. So those are like, phones and those stuff, like usually you are not allowed to have when you survey. So no magnetic stuff with yourself. Yeah, and here are some examples, like from marine survey, where you attach your sensor out to the boat. Here, like airborne survey, where it's like helicopter, it also can be attached to airplane, like these small ones. And newer trends in this like airborne surveys are UAV, so drones as a platform for, and this is something that we also developed partially at our university. I will show some examples a bit later on this. So, like for example, one case study, I could not really find resource for this right-hand side because I have it from my previous some lecture notes from long time ago, but I thought it's a very nice example to show you. So this is basically airborne magnetic survey, and you can see these stripes. So that's, we say, like we call it footprint of acquisition, where the airplane was flying. So we can remove it. So we also apply this general variations. When we apply general variations from base stations that we from a base station that we continuously measured, when we correct for that, so we see that footprint is less. And then we have tie line leveling. What are tie lines? Because usually airplanes would fly zigzag, but they would have also perpendicular tie lines for these corrections. And yeah, so we basically do several, like, let's say, processing steps to remove as much as possible footprint. And here there's one also from airborne magnetic map. This is from Sweden, and here we know it's a region with iron oxide mineralization. And you can see here these lineaments. These are some parts of mineralization can be seen, so on the surface. So this is already confirmed with another case studies, and I will come back to this example more in detail with another methodologies. But basically, you can see the magnetic lineaments overall, and you can see, okay, this is the strike. You can do some kind of interpretation, but the best is if you support it with more data before you judge. So there's also like round mag studies, very popular in archaeological investigations. You can see here one of the maps yeah, see, this is somewhere, I guess, in, I don't know where it should be. I just Googled for some archaeological map, but you can see that clearly you can delineate features underground. Usually, for example, here, buried walls, it can give the very outstanding anomaly. And yeah, many other artifacts that you can find, you can detect them. Also, like sometimes it happens like when you survey, because usually you would survey on fields like this. When farmers leave, for example, iron nails or something, like some machinery leftovers on the field, sometimes you don't notice it when you survey, and you get a big peak in your data. And it's very important, like when you process the data as such, it's very important to identify, is it only single value giving, like single point value giving so high value, and then once you can maybe sort it in your data set, and then you remove that one, and then you level your anomalies. So that's very important to take care of when you have such examples. Yeah, and then here there's some example I found that they wanted to map this trench, so you can see the differences in magnetic anomalies. So this is also ground. You can see their lines of survey, and then they actually extrapolate it between, and then you get map as such. Also, you can use many, like this data, you can filter them with different filters, and depends like what you want to enhance in the data. So I won't go too much into details on that, but yes, you can enhance some features even better, like to pronounce them sharper. So I said I will come back to the UAV study, and this is something that was conducted in mining area. Actually, this is a mine, iron oxide mine, which was closed in 70s. It is in central Sweden, and then there's one company operating in the area, and they want to renew interest in mining again here. And with them we have very good collaboration, and they also allow us to do many different kinds of surveys at this site. So we have a lot of data sets coming from this site, which is very nice, because we can compare previous surveys and new surveys. And in this survey, you can see here the lines where they were flying, and this is total magnetic field map, and you can see lineaments. So here should be our mineralization is this line here, that varies feet on the top, and these are like compared two maps in comparison. So one is from UAV, so that was measured UAV measurements, and the other one was like very old one from 70s, which was measured 30 meters above surface. And so we can see that these kind of platforms, that drone platforms, that they can have really good results as well. And what is very cool about this, they are not as expensive as you would imagine your car, like airplane, and you need someone pilot and extra stuff. So here, like it's basically, I would say, most cost effective, but you get comparable results at the end. And here more comparisons at the same site. So here you can see where mineralization comes to the surface. And here we can see also 4 different surveys. So this is what I already mentioned from 1972, where they fly fixed wing. So that's with airplane 30 meters above. And these are anomalies they obtained. So then next study, the same a fixed wing methodology applied, but this time they were flying a bit higher. And yes, because here is obviously like very strong anomaly, so it can be also detected here. And then again, there were helicopter survey in 2019, again 70 meters, and we see UAV 70 meters. So note here that it can go really high up, and clearly it shows very, very strong anomaly contrast compared, for example, with fixed wing anomaly, which is the same distance from the ground. But here you can see that it is much higher value compared to surroundings. So we can see really, really good contrast, and therefore, like from comparison, yeah, we can recommend, okay, UAV can be a good method and fast methods, although like you cannot really every drone, it has its own battery lasting, so everything has, you can see here pros and cons, like depend like on your project, but we can encourage this type of instrumentations to develop, and they're used, so it's nothing like breakthrough for this year. So we finished with magnetic method. I hope you got a general idea about the method. Now I want to mention a little bit about geoelectrical methods, and I won't show too much about it. I have, I think, only 2 slides on this method because I want to jump in on other stuff too. And yeah, so here I want to just show you the basic principle and one of the method techniques you can use for this type of, and also I want to show you one example. So you can basically have you have electrodes here on this on left hand side in this photo. You have one of the most commonly used instruments for geoelectric measurements. So you have basically these electrodes are like big nails. Let's compare them like that. And then you measure, you put every on the same distance on the ground. It's been a while since I was involved in geoelectric survey, maybe 8-9 years ago, but I still remember how we did it. So basically you put them along the profile, and then you have different arrays you want to have that you can electrode arrays that you can define in your main instrument. You can define which kind of array you want. So basically what that means is through which electrodes you want to inject your currents. So from this, for example, in this figure here, you have a Venner array, which means that spacing between electrodes is the same from where currents is induced and where is, let's say, measured. And then here from this and this electrode, we are injecting direct currents in the subsurface, and then on these 2 electrodes we measure that electric potential U, and then you can from those measurements, then you can get the distance. You have the distance between electrode, you have this potential, and then you can use formula to calculate your resistivity with rho. And this is the formula, for example, for this kind of Venner array, but there are many arrays that people are using, depends on the investigation. And here, if you look in this kind of table here, so it means like resistivity and rock types. So it's this method is quite used for groundwater exploration, I would say. That's something I've seen in most case studies. And you can see that where you can see very low resistivity and very high resistivity, like that we have in, for example, igneous and metamorphic rocks is quite high, and then in some, for example, clays, we can say it's very low. And while mentioning the clay, I can also show you one study that was done within our group. This is a quick clay landslide in Sweden. It is in this problem is very big. I don't know if you heard of quick clay, but it's a very big thing in northern countries, including Canada and Norway and Sweden. We have so-called quick clays, and it's a big hazard. And they even few days ago we had really big disaster in western Sweden. Quick clay, just landslide happened on a very major road, so it caused big attention in media. So we can say, okay, this method, as you saw, equipment is not very big for carrying around, and we can consider that you don't need so much people to conduct this. So conclusion is, okay, we can put this in a kind of cost-effective method. But what you can also hear many times, we have ambiguous results, which means that you cannot always be sure that this is it. For some things, yes, but okay, it can be this, it can be that. So you sometimes, for some case studies, you would go for supporting other methods with other methods. So basically, as you see that this is a landslide scar, and the profile goes from the bedrock, and here you can see a high resistivity interpreted as a bedrock. And here we have it towards lower resistivities. We say, okay, maybe because when we saw this range of resistivity values, we can conclude, okay, this might be from clay measurements. So that is what we could say from this data. But then, and this data set is also supported by reflection seismics done on the site. I just want to show you very nice integration of two. This is not joint inversion. This is just integration support of two different data sets along the same line. So one is you have one resistivity measurements, one geoelectrical measurements, one is reflection seismic survey. And here, we could define what is a bedrock line, and there are sandstone layers as well. And here we see that actually, in this case, are ERT anomaly, for example, especially for bedrock, to really show that contrast. So we can really see this. This is very nice example. Okay, I think I spoke almost an hour. I want to take a break a bit with you, and not too long, but I want to, again, if I kindly ask you, you're not forced to do it. I have a question for you, if you can write in 3 words, there are 3 boxes there and 1 word in each box. What was the most interesting part of the presentation so far? I would really appreciate if you can do it, because I will also later, I can share results with you. It is anonymous survey, so we won't know who voted for what and who say what. So please, but mind your language. That's my only requirement. So I hope most of you scanned it and answer. So I will move on to seismic methods. And this is the final method that I want to cover in this presentation. I will have something more at the end, but this is like from geophysical methodologies. I just chose these three because I thought like it's better to show something like less than go through all of them and everything a little bit. I think this was much better option. So here in seismic method, I want to talk about seismic reflection method particularly. And here on the right-hand side, you have very well known, like you will see everywhere in courses in seismic, how the waves propagates. So basically you have a source of vibration, which can be, in this case, you have a vibro size track, but you can have a drop hammer, you can have a sledgehammer. There are a newly also developed called e-vibes. It's like basically imagine like a big speaker vibrating, like that's like how it's based. And then yeah, so those are, then you have explosives like so there are different types of sources, depends what is your depth that you want to image. The stronger the source, the deeper you will see. So that's kind of the analogy, but yeah, it depends like what is the purpose of the survey basically. Like if it's very near surface exploration, I think you would not really consider vibro track, because there are many other things that influence like how much, but what is your budget? Like when we talk about creating and designing any survey, a budget is always a problem. But we always say, oh, it's better to do reflection seismic than boreholes. You heard probably that sentence many times. Like drilling is more expensive than. So yeah, I can say that like it's very good methods, provides very good resolution of the data. And here we can see like, for example, like we generate waves, wave reflects, and then you have like somewhere sensor. You have sensors along the line that they will receive that signal and record it. So it will, the wave will reflect in every boundary there is. And here, so basically what you get is then on the left-hand side, you have like a one-shot gather that we call. And basically this is like in time, because we measure in time. The wave comes to the surface. We call that two-way travel time. So one way, other way, second way. And this method, if you're in petroleum engineering, oil and gas industry, you would hear about seismic a lot, because this method was primarily like used, like enormously used for those purposes. But it's not anymore the case. I mean, it's nowadays we use it for many other applications, and I will show you. So I decided to show something different, because usually when you hear about reflection seismic, you will go for oil and gas and for some examples from there, but I will not present those. I will present something different, and there will be 2 case studies, but later about it. So basically here's your shot gather, and this is very nice textbook example. Unfortunately, I wanted to present here data set that we acquired in Denmark this summer. It was fantastic shot gather where you could see all different types and reflections and first breaks and so on. Like it was so nice, but I could not find it for here for today, and I'm so sad because it particularly took a screenshot to show you. But nonetheless, this is very textbook example where you can see, okay, this is your reflection signal, and then these are these are your surface waves, air wave, then first break arrivals, then this is like a refraction. So basically you can see, yeah, deeper reflections as well. We can also here identify not so strong but still visible S wave as well. So I won't go so much into details about it because you will have a session only dedicated to these principles. But I really want to show you examples. And these examples that I will show you, one is when you see here all this layered, like you can already imagine what is the environment. So it's a layered environment. It is sedimentary, from sedimentary. But I also wanted to show you something that maybe you are not quite familiar with it. When you heard in the beginning when I said like hard rock seismics, what does it mean? It means when you apply the same methodology, but in rocks that are not sedimentary, like when you survey those areas. So there will be also one example from there. So first study I want to show you, I got this data from my colleague Mirto, and you can find some of these case studies in her paper published this year. Yeah, so here is one study we conducted in Denmark, and we are still conducting. Actually, next week will be the final week of the project. So we were surveying several sites in Denmark, and I will show it on the next slide on the map. So basically, this project was about finding suitable places where we can store CO2. And yeah, this was a big initiative by Danish government, and with the Geological Survey of Denmark and Greenland, we managed to conduct really nice project. So the mission of Denmark is to reach carbon neutrality by 2050, a very ambitious goal, and that's why they have very extensive surveys, and all of this data will be public. I think maybe some parts of this data survey are already public. So maybe, who knows, maybe some of this data will be provided for next year hackathon, because there's a bunch of data and it's very nice. So this is one of the sites from a drone photo. You can maybe identify the seismic source. We had the 2 vibroseis trucks, and we have this line that you see. That is what I mentioned in the beginning, the state-of-the-art lane streamer system. I will show it more as we go on about the system itself, how it works. But also we had along the line, I don't know how much you can see, but these white dots here, those are nodal arrays, so wireless stations placed along the profile. So basically, in the old times, like maybe, I don't know if people are using it still, but we had, I used it when I started my PhD. We had survey with cables, and that was very painful, like carrying all the cables and then planting then geophones and cables. It was so heavy work and so much physical work. But now it's much more like facilitated as technology is developing. We have wireless sensors, and market is full of different solutions, like in terms like what is effective light, or like how long your battery can last in the field, what is the storage of how much data you can store, because like what I'm talking here is active survey, but what you can do also is passive surveys. You monitor constantly, so that also stores a lot of data. So there are like several different types of sensors you can find on market, and they're competing, like who is providing longer duration of battery, of what is the storage itself. So but everything has, of course, pros and cons, and I won't go into details in that, but just I want you to get feeling like how the technology is advancing every day, even in geophysics in general. So I want to show you, like, this case study is, you can see on the right hand side are these blue areas, are the areas where Danish government wants to conduct survey, and we already surveyed in this Stenlille part, and now I will show this Hanso part is the second survey we conducted. We also completed Gasum, the biggest survey. It was 250 kilometers, and the Rodby this summer, and now we're completing this part, Thorning. These are the line sets, so there are a bunch of 2D lines, and you can see they're not straight, they're crooked. So we used all possible roads where you can survey. So there is also one part was also marine part of the data, and also one part is shot on this island. So they wanted actually to extend the knowledge on the formation here in this part. So basically, this is the setup, and these small lines here you can see is the pilot study we conducted first. So you can imagine what is the scale. I think this survey was 130 kilometers, give or take, and this one is about 12 something kilometers. So you can see this huge upscaling from one survey to another. This was just a pilot study, and then we went right into this large-scale survey. So let's see how we did it. So here is the nodal unit that we used. So basically it's a geophone. So this is geophone data, and this is wireless sensor. Spacing is 10 meters between. And what we had, another in parallel sensors per so-called like our lens streamer system, which we trademarked for SaysMove system. So basically the system contains 3-component MEMS sensor, which is different to geophone, is less sensitive to such noises. And the system is actually working like that you see here sleds, this yellow part. It is made of very high resistant material, because as you can see we are surveying on roads, and you want material to last longer. So basically we want something that won't worn out easily, and that's the system that we use. So basically we are dragging it as we move, so we are shooting at every point. So every point is our nodal point, so we are vibrating at every nodal point, and then we move on as we, like, every point we vibrate, and we move on to next, and the streamer is sliding behind. So basically here this blue thing is the trolley between two segments. So every segment has 10 units, and in between units is 2 meter spacing, as you can see here. And this is just simply we put here equipment that will power the line so that it can transmit signal to the recording. And here we can see there is operator sitting in the vibe, and we were sweeping 3 times per each point. So basically, yeah, so that is continuous process. And yeah, so sometimes, like, it depends how many, not always we had all the segments. So we usually tend to have 5 segments. That's 5 times 20 sensors, 2 meter spacing that are dragging behind. But sometimes, of course, you can assume challenges in the field, and that we are sometimes going not only on the asphalt road, but also dirt roads. And if a road is curvy or some other challenges in surveying, of course, we we will cut maybe some of the segments, but we usually don't do it if not really necessary. So here I want to show you some of the data that we obtained from this survey. So you can see from nodal array, so that means what is recorded on the wireless stations. And here something from land streamer, what is recorded, what was dragging behind. So you can see, obviously, why is this shorter than this shot gather? Because what we said that we had, depends how many segments, how many recorders dragging behind. So they are limited numbers. Whereas here, we usually tend to have spread at least 700 meters. So that's usually what we tend to do, but sometimes it's longer as we move on. So this is some examples like where we can identify some very like near surface reflections which indicate better by land streamer, and that's why we combine them. Actually, I didn't mention why we even bother to collect dual data set. So one thing is that with land streamer, it's shorter spacing. We wanted to have to achieve high resolution at the near surface, very near shallow subsurfaces. And with nodal, we noticed that the better quality is in deeper parts. So that's basically how we combine. So when we combine both data sets, then you achieve that high resolution in the near surface and deeper parts. So some of the processing steps. So here I already showed comparison, and now here is the raw data, and then when we apply some bandpass filters, bandstop filter. So basically you want to retain these frequency ranges, and bandstop remove some certain frequency peaks they saw in the data. But I won't really go into details with it, because you will have a dedicated session to all of these issues. I will just show you, because this is some of the workflow developed within our group that was later adapted for other surveys in the area, more or less. So yeah, this is just for you to see that we are interested in these reflections here. And then they are we see every processing step, enhance them. So that's actually the main point. What do we do with all this stuff and filters? So we, as I said in the beginning, we want to increase signal and suppress noise. So we want to enhance these reflections. And yeah, so later on, a bunch of other stuff. I don't want to bother with that now. This is one of the sections. And here is one of geological maps that we got from, I think, from Geological Survey of Denmark and Greenland. And here is the position of one of the boreholes that we can see the boundaries of the data. So this is the only section obtained from nodal. So that means only from wireless stations. And here now we have, when we merge, so I said we have, this is profile 1, and profile 1 also had this marine part that was not conducted by us. So that was from GEOS, from Geological Survey of Denmark. So these parts all together merged. And then we can see here cross-cutting line, another line, and how they follow each other. So you can see that the reflections are, you can identify the same horizons in all the lines that I'm adding now. And now when we look from above, you can see which lines I'm adding. So these are the lines presented over here, and then we can clearly identify horizons that they're a good match, and so on. Like for example here, and so on. So yeah, so here finally you can see that we could identify all horizons that we were interested in. And then like this is from some previous surveys, so this is like the open structure where they want to like expand knowledge on, and I think that these are older data from I think this was some 3D survey, no, 2D seismic lines, yeah. And yeah, these were older data, and this is like how it's interpreted. Yeah, and then we found like all the horizons that were supposed to correlate with this legacy data. Yeah, so basically this is one of the examples. So they wanted to see where the dome extends and more knowledge, more, I mean, these are still preliminary results. Our team is working on further improvements and different aspects of this data set. So few papers have been submitted on this data, and I hope they will be published next year, revised and published next year. So there will be more on this topic for sure. But this is just like something that my colleague, she gave me this for presentation, and I thought it's very nice to show like some kind of real examples and what we do. I thought it's very cool. So this is one of the example. Another example I want to show is for mineral exploration studies, and this is actually the same study place where I show you the UAV mag measurements. So here I want to show you reflection seismic study that we conducted. So this line from red line and yellow line, that's the seismic, 2D seismic done on this place, and you can find it in this paper, more details about the survey. But what I want to really point out here is you saw in the data, in the shot gather, I showed you that this textbook shot gather on the very first slide for seismic method. You saw this reflection, all nice layers. But when we come to hard rock environment, you have to forget about it. We don't have layers in terms of like boundaries, but we can have reflection in this case because iron mineralization, because we have layer of magnetite and hematite, high concentration of iron, we can see the reflection from the mineralization because density is higher than the host rocks, right? And here we can, this is raw gather, so nothing was done of processing steps whatsoever here. And already here we can see some signatures, reflection signatures. And then when we move on, this is refraction statics. So one step, another step, like when we apply some filtering. Here we've applied some other filtering I won't bother with you about. But basically what we wanted to remove here are these strong surface waves. Let me go back, like this strong presence of surface waves. And yeah, and then you can see now clear signatures of reflections that comes from mineralization. So basically when we stack migrate the data, here also some boreholes logs done a few years ago, and we can see clear contrast in density because I said it's iron oxide mineralization. It has higher density compared to surrounding to host rocks. So, which you can clearly see here, high peaks in density logs. And yeah, here we can see horizons of hematite, magnetite, probably. And we also identify other reflections within the data, which we interpret maybe that comes from some fault system or maybe another mineralization, which we will argue later in several other case studies that are published on the same in the same area. So here is the model, because I said in this place they had a mine before, like until the 70s. I think end of 70s it closed because prices of iron dropped down and they closed the mine. But then this company, they wanted to open it again, and this is modeled from the boreholes, and this is like the horizon, the depth to which is known, that's known mineralization. And here what we wanted to do is to see whether this mineralization continues deeps more than we know, because there is no borehole information on that. And if we go back, and you see here that is a reflection continuity dips down, actually, we can argue that, okay, that can be deeper part of mineralization. And even more, we have this underlying reflection that can be as well perhaps some other mineralized horizon, because it's the same it has also pronounced, like it's strong reflectivity and compared to the surrounding. So basically, yeah, you can see that this is up to 800 meters, and we can add at least 200 meters, 300 meters more to this depth. So once we did 2D studies, okay, we said like, okay, now it's time to do something 3D. So I will continue the same site. So what we surveyed here is so-called something that is not really conventional to do. It's called sparse 3D. What is sparse? That means sparse means that is not regular. So you can see usually when you think of 3D surveys, you want regular grids and so on. But here, what we wanted to also achieve here is minimal environmental impact. You can see here forest. It's a forest area. So what we could use here is actually forest roads and any like asphalt road that is in between, but there are not many of them. So all those roads, dirt roads, forest roads were used. And these red lines, they are lines where we have receivers and where we were sweeping, because source was 32-ton vibrator, which is enormous, enormously huge source. Then we had here combined cable and wireless system. And here it's a road, but we couldn't shoot because this road was not permitted for vehicles that were heavier than 18 tons. And this was one of the challenges that we had to face, because we had really, really big source of seismic vibration. So yes, now let's see, this is the area that we surveyed. This is the setup. And here are some shot gathers. So we can see already in a raw gather that there are some reflection signatures that can indicate that they come from mineralization, and we know that what we can expect from the 2D survey. And this is shot on line 8, that is somewhere from here, from this part, and then recorded on all other. So one shot here and then recorded on all other units. Then we can see, like we did refraction statics, and then combination with 2D, 3D. That's like some tricks were done there, but I won't go now into details of that. And then after a bandpass and some other filters, we could see more distinct reflections here, like 3 sets in this part, and we could track the other ones too. And yeah, finally, when we visualize it in 3D, so this is the historical borehole, which is said is the deepest borehole that reaches the end of this model of known mineralization. So there's no information in this part. This is our survey line, and this is where the mineralization goes on top. And if you remember from the mag map here, we had these lineaments, right? So this is leader date actually on top. So these are, if we compare 2D lines, so we say, okay, this mineralization has indicates that there is continuation, like based on this data set results we obtained, that it continues with depth. But let's see now what 3D survey says. So this is unmigrated, and then we can see here that reflections are seen in deeper parts, in volume. So now we can see lateral extension of mineralization. Then with 2D you can obtain direction more or less, but with 3D we want to see also the aim of this survey was to see, okay, how much we laterally if we have a depth extension. So we can estimate the volume. And once we migrated, so migration is also one part of data processing, but you will be introduced that soon. We put everything in place, and we see here some interesting shapes here, structures like a bowl shape structure, maybe some kind of folding happening there, and we see that mineralization extends with volume. We can identify some of the weaker reflections that have kind of that can indicate on some fault structure, but it's still very weak to represent. So what we did to compute the volume of the mineralization that can be additional resources to the known one is that we pick, if I go back, we picked all these high amplitude shells within the volume. And then what we could assume from this is that that potential resources are dipping down approximately 300 meters and laterally 300 meters as well towards the west, so towards this side, and also that there are underlying resources there. When we put that together, we added also potential fault planes. We see it like this, and finally, like we can present it in a way of a volume. So here, our block model, so-called, that this is approximately calculated that it's about 10 megatons. And this case studies actually help this company that operates within the area to get more investors. And the most recent news is that they will actually open a mine in a few years, reopen a mine. So they're like now in also process, they will open many workplaces for mining engineers, also all geoscientists. So it will be very it will be a place with many positions to apply. And what I also didn't say here in this interpretation, you can see that using this topoline, we can see topolineaments that can indicate the strike of the fault in the data, but this needs like further exploration, and they will expand their exploration in these areas. So they are soon, I think next year, they have a project to do additional drilling campaigns. So it will be very interesting to see what comes out of it. And now I want to go to the final part of my presentation. As I promised, I will say something about AI implementation in geophysics and some case studies. And you can see here, I really like this spot robot dog. And this is our photo. It doesn't bite yet. But it's very interesting development. It is not new though. Boston Dynamics, the company that constructed them, used them long time ago for other purposes. But here is very interesting purpose. You can see two spots inside of the mine. And it's very nice application because they can go ahead, instead of humans, map the hazards, and also, for example, they can, if I'm not wrong, they can also measure radioactivity levels and also methane. So they have sensors on themselves that they can measure all these changes, and as well there's a camera on front. As you can see, here is the front side. There's a camera on front that can map everything, like in the mine galleries, and if it's safe to operate, like for example, after blasting, they can send a dog rather than a human, so that will minimize harm. So that's, I think, very, very nice advancements when we talk about robotic applications in earth sciences and exploration. So then another one, as I was mentioning many times, is drone platforms. And this is anechoic room where they were testing MAG UAV. This is within Uppsala University facility, I think, for physics department, if I'm not wrong. So yeah, this was one of the testings, and I mentioned many times that it's very also good, nice advancements in geophysics in terms of hardware. How can we survey with less manning power? So that's very nice application. And then I want to go about like into AI and data and some other case studies. So this is one of the case studies that is from part of my PhD. It was part of my PhD work. And here we have synthetic seismic data. And what we wanted to do is to to recognize diffraction pattern within the data. So you can imagine like this kind of application is like a pattern recognition, for example, but we can transfer that also in geophysics. Originally, this kind of deep learning, I would say, that is not anymore machine, it's deep learning method, was developed primarily for mapping cancer cells. So it's in biomedicine purposes. So they were the first ones who came up with the idea and the structure of the whole segmentation. So here the purpose was to recognize the pattern of diffraction. How we did it? It's we had the ground truth, what we call the ground truth. So you have the clear representation, what is diffraction, and then you have like here, these are the patterns that you want to recognize, and then your algorithm learns from it and tries to find it in the data you give it. So this is with zero noise, and then I've added some random noise in the data, and you can see like the differences in recognition, because here is only like image, so we convert seismic data to image. I will say a little bit more about the methodology itself in the next slide. And then we can see like what comes out. So we can see some of the red spots here. It means that some of the pixels that were that belong to noise were recognized as diffraction signals simply because those pixel intensities were found within these diffractions, like here. So that's the reason for it. So when we have a lower noise, there are no many like false solution, let's say. But when it's higher noise, we can expect something like this. This is basically the structure I just explained, and this is how we did it. So we had seismic and GPR sections. So I will show you also GPR example. That's we converted to image because I wanted to look also in GPR diffraction and seismic diffraction. And then you build a model for diffraction recognition, because we annotated all the models, all the diffractions in the section. Like when it's, I will show you when it's a real data, you have the program where you have to click around and manually annotate every diffraction. It's a bit painful process. That's why people are less and less keen on it. But yeah, I had the podcast on in the background, so it was okay. It was not as painful. And yeah, so this is basically the structure of the so-called UNet. So you have input, and then we have a big section. We break it into tiles, so every tile become one layer for learning. So you basically algorithm is learning to recognize patterns in the small, like in the smallest tiles of the section, and then the next stage is like its prediction, and then you have the signal output. So basically what program learned from your algorithm, what the algorithm learned from your setup, like how did you, like you can of course play with these things, improve it. So basically it's like iterative process, I would say. And here was the ground truth corresponding mask. Here is the prediction. And interestingly, here you can see this is GPR data set, very strong around the apex. So that's like, if this is diffraction, apex is this part here. So this is called the tail of diffraction. So here, for example, in some of these parts, I didn't even pick anything, tails, nothing. For example, this part I didn't even pick, but algorithm found it. And that was really, really encouraging result we got. So you can see here more in details, like application of UNet for GPR. I think we got this data set. I mean, we use it just for these purposes. We didn't say what was surveyed, but I think this was the graves. Every diffraction is actually response from the grave, if I'm not wrong. I think that was the purpose of this survey. So anyway, this is what I did, annotated by hand. So I picked polygon around every diffraction, and then I pass it through the algorithm. Algorithm broke it in these tiles. So you define the size of the tile basically. Here's your ground truth. This is what was predicted. For example, here, extension of the tails. Diffraction tails here, as I said, like this part was predicted and it was never annotated. But in some cases also like parts of this reflection, because it's like it has the same intensity, because we convert this in pixels. So I will talk now as a pixel intensity as this part here of diffraction as apex. So it would consider that it follows into that range, and therefore like it can be confused. But overall, when you see the results, it's quite promising. Of course, they're like, you need to make this work really good, you need a lot of data sets. So basically what people do, like you don't have as many, I mean, you can have, like if you have a lot of data sets with diffraction, you can feed them in the global model and then you can expect better results. But this is just trained on this data set. So having that in mind, I think this was very good. So if you can build a global model, you can take any data set anywhere and then train it. And then, of course, you will improve the performance. And another application that I want to talk about is applied on another, again, a hard rock seismic data set. And then here we have one very nice pronounced diffraction signal, which I annotated. And here we had difficulties because this is 3D data set. So I looked only into this we call inline, this is cross line, and this is time slice. So just for the reference. So I didn't have so many inlines I could extract for machine learning. Therefore, it was like already a limitation of the method. But what I did, like, okay, this was the optimal parameter input, like these were the tile, like small overlap between them. So basically you cut your section in this dimension, and then you cut every 60 pixel the same dimension. So you create about 8,000, this created about 8,000 tiles from all the inlines and these tiles we had. So basically what happened then, these are some of the results. And we can see that here, like ground truth and prediction were very nicely comparable. But when we come to some other parts, for example, in this part, we were always mapping this feature, and I will come back to this, which is very interesting. And this feature was never annotated. So I showed you I was only focusing on this one. And where we didn't have any annotation, it was really nice. So we didn't have so many nonsense picked. So it was performing quite well. So it was very good that this was 3D data set, because we could go back into the cube and look. And we say, okay, is this maybe an incomplete diffraction signature because it's being picked up by the algorithm all the time? And this was never, like in previous publication on this data set, it was never mentioned that this is actually diffraction. It was interpreted as a reflection. But let's see now. We modeled in 3D. This, like we modeled as a point diffractor hyperboloid, and then we modeled another one. So, and it fit in inline crossline time slice, but the apex, so the apex is outside of the cube. So if we add another, so what can we conclude it with? Is this maybe diffraction from another volcanogenic massive sulfide body, EMS body? And this diffraction apex occurred approximately 500 meters away from the cube. So that can be very good if they want to expand the exploration in the area. It can be a very good place to set first targets for exploration. There is no additional data on that side, and this would be very interesting to confirm. But yeah, when we went back to the cube, it was obvious for us that this was actually an incomplete diffraction signature case. Another case study, and with this I will wrap up my talk. This is a case study where I told you on a previous example I had to pick everything by hand, but in this type of machine learning, I didn't pick anything. So this is so-called autoencoder, and here I just applied, I mean, I'm showing several examples, not all of them. I applied to kind of denoise the diffraction, so to enhance diffraction signal only. So basically what you do, you train the algorithm with only clean representative of your diffraction. So it doesn't need to be annotated, just have as clear as possible diffraction signal and then pass it through algorithm, and algorithm might recognize. So this is basically what a strong single diffraction, one of the tiles, and you can see what was predicted as noise, and then this subtraction between two of them. You can see clearly here diffraction, but not this reflection part. And even better example here in this part, like this is another tile of the same section where we have only tails of diffraction, but look at them how weak they are compared to the surroundings. So you cannot really, I mean, you can see them, but it's still weak, but not for the algorithm. Surprisingly, it didn't touch any of these parts of the tail. It actually separated it completely. And also probably these other crossings here, like for example here, see maybe it's some weaker diffraction signature, which is super cool. And here is something on synthetic data that we did, and there is like a strong noise. And here's comparison when we subtract in image domain and seismic data domain, pros and cons. Basically, here we lose the data because the noise, predicted noise, actually has the same, in this case, amplitude value, but here it goes to negative pixels, so it can preserve the whole signal. And especially in this part where these diffractions are crossing each other. And yeah, this is basically similar structure to UNet, because this autoencoder is built on top of UNet, but I guess you will hear more about machine learning and deep learning in a special session, but this is just for you to give an idea how you can use it in your data also. But there are many other ways, and in seismic data there are a lot of different applications of AI, not necessarily regarding, this is like a pattern recognition, so it's not really specific. There are many other methodologies really developed, and I see papers published on a daily basis, a lot of them. It's quite a trend. So it's basically we're the same, just what we have as an input, as I said, it's a clear representation. So this is what I had, for example, for this GPR data set. This was the input, this was what I was training the algorithm with, and this is the output only signal. And how did I get there? So this is GPR data surveyed on along the bridge deck, and along the bridge deck, and then you have this diffraction response. And then this is the noise predicted from the autoencoder algorithm, and you can see here, because we broke it into tiles, it's obvious this tile footprint, but that can also be tackled in other, like there are methodologies how to get rid of it, but I don't have it here. Yeah, so basically you can see that not really diffraction signal taken here, and as output, like when we subtract these two, we get signal output here. So it's a very nice example, I must say. And with this example, I want to conclude that you got a lot of information to take in, but I hope you enjoyed. And I have the last one, I promise. This is the last question for you. Like, I want you to scan this QR and again write one word in each box. You have 3 boxes there. What was the most interesting part of this presentation overall? And I let you hear. Yeah, thank you for your attention, and I'm ready for questions.
Thank you very much, Magdalena, for that interesting presentation. Kind of took us on a journey, and what was really nice was, you know, the personal touch of the projects you've been working in. So thank you very much for that. I will admit that the audience seems to be a bit shy. So we did not get questions in the box. That could be that they really understood everything. But
I'm glad if so. I hope they answer at least to my questions here, so I can get some feedback.
feedback, yes, no, absolutely. So we'll leave the chat open for questions, but I do have a question for you, if you don't mind me asking. You were
Absolutely.
talking about the seismic methods, right?
Yeah.
And so the whole idea is to try to understand the travel time and the reflections. The question, at least, I guess, would be, if you're dealing with an area that's very laminated and there's all sorts of changes of densities, layers, rather than like homogeneous big layers, how
That's
how
how we always
complicated does that get for you?
well, you can see that in data. I mean, now the more experience you have in seismic processing, but yes, obviously, like you can see everything in data. Like there will be something depends. Like really it's case dependent. Like in that case, I would say like once you show a shot gather, you can already tell more or less about the structure. And also like it depends like what is your source, like also that can give quality of the data. So it can, of course, geology can affect sometimes on lower data quality. For example, in seismic data sets, there was one case study where there was I think in Zambia conducted. So they had a package of, I think, 300 meters that was like a weathering layer. Imagine that. And then like it goes like bedrock. So they were putting, I don't know how many kilos of explosives to reach the depth, but they couldn't really achieve so much because it was a dry season. And then like the weathering layer was very thick. So those things like you have to account when you go and survey in very challenging places, like also, yeah. So it's a really case, and you learn from those case studies. I mean, even failed case studies are good case studies because you always conclude something. Okay, this I learned now. I probably won't do it again. And I think I always encourage also, like sometimes I think in publications in journals they should publish also failed case studies because it's very good learning process for many. Yeah.
Absolutely. I think what you said is very important. For sharing knowledge, failures generally lead to optimization of things, and that's kind of how we learn. If we are to showcase all the successes, that is a great thing, but we have to think of ways to improve things. So, well, tied to that question, I guess, let me ask you from your experience, and then, okay, before we move there, we have a question from Robert. It says, in gravity survey, how does one discriminate between a density variation driven by heavy metals or lithification?
Yeah, I wouldn't really know how to answer these questions because I'm not a gravity expert, but I can maybe always encourage that in gravity surveys, usually we want to not do them only alone themselves. So we usually alongside we tend to do mag surveys as well. So I can that can be my answer to the question.
Okay, so it's a combination of
yeah, usually what you would
data.
combine, like because with potential field methods like gram mag, geoelectric, like you can, it's very, as I said, like sometimes it's very ambiguous, so you cannot really conclude surely like what is there. You can get some idea overall, but I mean it's not that I'm biased because I'm in seismic, but like it's just combination is always good in that case, I would say.
Oh, absolutely. I think that makes a lot of sense, right? I mean, in the industry, if you think of it, when professionals look at logs, they try to look at different kinds of logs to try to come to a conclusion about a zone, right? So I guess this is what you're also saying.
And absolutely, like when it comes to like data interpretation, as I said, like you have to integrate all the knowledge. I mean, it's not only, oh, I'm seismic, like my reflection is that. You have to always verify it. And of course, we said like drilling is verification, right? Like once you drill it, you see the core, but you cannot, like at some depths, you cannot drills. And of course, like some places are very challenging to conduct drilling, but we can get a feeling like from those like studies, like what can we expect, at least like what we saw in this horizons change, like what are different contexts of what is the difference between layers, like what we contain in each package. So those things gave us feeling, but like as you said, like before everything, like budget is first thing to think about. And we know that drilling is very high cost method, and that's why when we talk about geophysics in general, like geophysics is very good tool to narrow down places where you really want to do your work, like for whatever is the target, even like geothermal energy as well, because then you can eliminate, okay, I don't just drill blind because I think from the surface geology that that's it. No, I will do some more investigations, and then I will go, okay, I will narrow down, say, okay, this is it. You can drill here. Better drill where is the narrow down than just like blind. That's my...
Yes, blind drilling is not something that, let's say, management likes in the industry.
And
So
it's really costly method, so you don't want to just
absolutely.
waste.
So we actually have a couple more questions that came in, Magdalena. So one of them, it says, fascinating presentation. I have two questions for you. So when developing the CNN for diffraction prediction, how did you decide on the different aspects of the layers, like kernel sizes, for example?
Actually, I have to say that I did basic ones. Like I was, those sizes I just took from, because I was very new in that area. I just took from examples I could find, and I just saw that it worked well for me. And that's how I used it basically. But I didn't really do so much of tuning in that regard. I was mostly, when I was applying the algorithm, mostly I was taking care, okay, how large the tile, how much I can capture the signal pattern within one tile, and then when it decreases, how much will be captured there. So to avoid this false picking of signals somewhere else, so to be more narrowed within the section. So that was how I would explain, but not really that. Some parameters, of course, there are many parameters in the algorithm that change, like I don't know, learning rate and so on. I now even forgot a lot of them. So there are other things within the algorithm that you can change and tune. So those things I did. But basically layer number, I thought also it's very important, because computational power is also one of the issues. I mean, you can add more layers, you can play with it, but also like it is consuming computational device. So you have to see like what is your limit. For this particular study, I used Google Colab, and I had to shift to Google Colab Pro because it didn't have so much memory. I had the memory issues and I could not run all the algorithms. So from in that regard, like if you want to do some training in deep learning, you can use Google Colab. It's very well recommended and it's very well organized. I would go for that.
We're going to get a lot of that information coming from the next sessions from next week. Once we start getting into machine learning. I like that there is some kind of interaction in the chat box between our participants. Remember that we have the Discord channel, so you can also use that to talk to each other. We have a couple more questions that came in. Sarai asks, what was the approximated size of your training data set?
Oh, for which data exactly?
So Soraya, if you don't mind clarifying in the chat box for which case study example you're talking about. Meanwhile, there was a question that came in and said, could you explain the reason behind the aurora phenomenon again?
The reason, okay, I came back. First, I will answer to first question for machine learning. I can go back.
She says it was the last one. The
last
case
one,
study.
okay.
Yes.
Actually, for example, for this particular case, I had about 20 sections of this GPR, 20 GPR sections, and half of them I actually trained. I think I trained 8, but as you saw, I broke them in the tiles, and then small overlap between the tiles, so that creates a lot of data sets. So every tile become actually your one data, part of the data, and that it runs through the program. So I don't remember now how many tiles it was, but as I mentioned in the previous example, that we had like a tile size and then a small offset, and that's how I create a number of tiles, and then that actually enlarge your data set for training. And now I can go back to, I don't remember now which slide it was.
The Aurora. I think it was like at the beginning.
I can look like this and then scroll back because there were many slides. Okay,
yeah.
I hope it's this one. Yes. Okay, so our Aurora lights, phenomena, as I said, it happens when you have strong solar activity, and then strong solar wind comes towards the Earth, and then it disturbs magnetic field lines, and then part of it goes through the poles, like it comes in the. So basically, there is also something I didn't mention, but it's very hard to explain because I don't have complete picture of this tail, magnetic tail. There is one thing that's called magnetic reconnection. That means that when you have this strong solar wind coming, so on one side, as you see, field lines are pressed, and then on the other side is elongated. So when you have a strong solar activity, those lines tend to connect. So these two parts, they tend to connect, and then part of that energy comes to the poles, to the magnetic poles, part travels in the space. And that energy transfers, like in the Earth, comes to this radiation belts, and then later what is left over comes to the Earth, and then when it mixes with different gases in the ionosphere, if I'm not wrong, it becomes that light. So basically, it is due to solar activity. You can see them, and I mean for southern hemisphere, of course, it's very hard to see it because we don't have really southern point where you can go, like where people are really living and where you can go and observe it. So that's actually why Aurora Borealis is more popular than Aurora Australis, simply because it's very hard to find a place where you can see it. You really have to go south. But
get on a boat. Get on a boat and start sailing.
Yeah.
Thank you very much.
Well, it's like they can probably on Antarctic stations, they can observe, maybe also South America. I mean, I'm looking now at this map.
Yeah, where Argentina
probably
is.
Here because
Argentina.
Yeah, we can probably on these latitudes we can observe it, but it depends. But yeah, so that's why like it's more popular on the northern hemisphere.
Okay, thank you very much, Magdalena. We answered Sajad's question. We have Soraya, who thanked you about the presentation, and then Alex Mocano, who asked a little bit, like, what are usually the limitations, like the maximum depths for the methods that you presented? Let's say, the magnetics and then the seismics itself. Like, what are the current limitations based on your experience?
Yeah, that's a very good question, I have to say, because I would say, like, what you want from your data is resolution. So good resolution. What that means that you want to define the boundaries, you want to define your anomalies. So I would say like some methods, they have very good resolution in a very near surface, therefore they are applied there. But for example, seismic method, this has very good resolution with greater depth. So then if you want to look deeper, you would go, because resolution increased with depth, you would go with seismic method. If you want to look in the shallow surface, you can subsurface. You can, for example, what they showed in magnetic method here for archaeological studies, you can really get pronounced anomalies like in the near surface. So I would say like that seismic method is very powerful when it comes to resolution with greater depths. So that's why it's used in oil and gas exploration, in CCS now, mineral exploration as well. Like it depends. Now it's also, I want to answer this question. Like someone might ask, like, but what do you consider near surface? What is the depth like? Well, we have like, because I'm coming more from mineral exploration side, we have a saying that near surface is where a man can go underground. So, but when you think of it, we have mines that go 3 kilometers underground in South Africa, and recently we had also seismic survey 3 kilometers underground. So basically, I don't know if you can put that as a near surface compared to other stuff, but let's say like this, some shallower also mineral exploration can also be within near surface range. I would say that this Ludvika in Sweden, this mineral exploration study that I showed, that can be classified as near surface exploration.
All right, so different types of investigation, combination of all of them to understand what's going on. You take into account the depths and the type of methodologies that you're using. Keep in mind what your goal is, and in terms of at least that intro on AI application is, I think that's gonna get a lot clearer for our participants as we go through the next week. What I don't see in the chat box is any more questions, so we have come to a close. I would like to tell the participants that the next session will be on October 9th, and it will be on seismic data processing, right? So now we're going to start getting more in depth. You got a sense of geothermal energy, how seismic is used. Magdalena today gave us an understanding on basics of geophysics and the methods. And what we're moving to next is, okay, we've acquired some data, but what do we do with that, right? So how do you process it? And then as we move through the weeks, we're going to go into machine learning methods and interpreting that data, which will all hopefully help you at the end with with the hackathon challenge itself. So if there are no more questions, which doesn't seem so, I would like to thank Magdalena again for being part of this. We appreciate your time and your willingness to, share the educational knowledge. And we will all see you on the 9th of October. Stay tuned, stay active on Discord, and get a hold of us if you have any questions or you need anything. Yes. Thank you, everyone. Thank you, Magdalena.
Thank you, Gabriel. And thank you all.